okay? So the only point, again, is that, yes, exothermic reactions tend to be considered automatically to be spontaneous. There are endothermic processes that are also spontaneous. And so, sorry about this purple. I had no idea it was going to be such a bad contrast color. So now we're going to talk about entropy. So one property common to spontaneous processes is that the final state is more disordered or random. Again, we have these words. The final state is more disordered or random than the original. So spontaneity is also related to an increase in randomness. Okay? So we have two things that are favored as being spontaneous if we have an exothermic reaction or if we have a more disordered or random state than we had before. And so we have to take both into account. Spontaneity is related to an increase in randomness. The thermodynamic property related to randomness is entropy. And so if we again look at this ammonium nitrate, if we look back at our ammonium nitrate becoming a solid, even though we have to put heat into the system, this reaction happens because our increase in randomness is what drives the reaction forward. So yes, it requires heat to occur, but at the end of the day, what do we have? We have a more disordered state. We started out with a solid, and here we have ions in aqueous solution. This is much more disordered, much more random. And so even though we had to add heat, it was an endothermic process, the driving force, what we call the driving force, we can say that either a reaction is driven by enthalpy or driven by entropy. What causes or drives this reaction to happen is that we're forming ions which are more disordered than our original solid state. Okay? All right. Excuse me. Over here on the left, we have the reaction of potassium with water. If we react potassium solid with water as a liquid, we are going to get KOH plus hydrogen. This is soluble in water, so we're actually going to have K plus aqueous plus OH negative aqueous plus hydrogen gas. Okay? So we started out with a chemical that was in the solid and a liquid, and we got ions and we got a gas. So in this particular reaction, and you'll see that there's a lot of heat given off, this is exothermic, and we get a positive entropy change. Why do we say we have a positive entropy change? Because our solid and our liquid gave us ions and a gas. Okay? The entropy of liquid water is greater than the entropy of solid water. I'm going to come back to this for those of you who want to write it down. I just want to look and see what's next. Okay. And so we can make a general statement. Let's make the general statement here. You have solid, and you have liquid, and you have gas. Okay? Anytime you go from mainly solids or mainly solids and liquids, to products that have liquids and gases. This is increasing entropy as we go up. So a solid is much less disordered or random than gases are. We've already said that. So the entropy of liquid water is greater than the entropy of solid water or ice. Okay, so here's our summary. Some of the questions that you're going to answer are just going to deal with a given chemical reaction, and you'll be asked, does entropy increase or decrease? So these are our general rules. Probability suggests that a spontaneous reaction will result in the dispersal of energy or of matter or of both. So we can disperse our energy, we can disperse matter, or we can disperse both. And so if we're trying to figure out how probable reactant molecules will react, whether we're being asked to analyze a chemical reaction, or whether we think it would have a positive entropy change or a negative entropy change. Sometimes we're asked to pick the chemical equation that has a positive entropy change. Then we are looking for how energy is dispersed, how matter is dispersed, and sometimes both of them happen in the same way. So if we have matter dispersal, what does that mean? It means that if we could have some kind of a system whereby all the gas is confined here, and this is a vacuum, and we open this, what do you know is going to happen? You wouldn't even have to do that chemical reaction. Just tell me what's going to happen. The gas will disperse. And so what would we observe over time? We would observe this color becoming lighter. This would no longer be clear. It would have these molecules over here. So that's an example of what we mean by matter dispersal.
Would it equalize, or would it become 50-50, or is that very dependent on the conditions?
Well, whoopsie. So like if you could actually measure the molecules, right, they never stop moving, right? So at any moment in time, we could have like 51 over here and 49 over here, right?
Yes.
Okay. And if we held like a Bunsen burner over here, that would probably drive some over there. But all things being equal, they're going to be about 50-50.
Okay.
Given the context that they're always moving and they're always going to, 52, 48,
Close to 50.
Mm-hmm. Yep. Yep. Okay. If we had a molecule that had potential energy and it underwent reaction, and that energy is dispersed, that also represents an increase in random